Saxon's Calculus, lesson 43 is about an antiderivative, and then our second calculus concept of integration. So antiderivative is trying to tell you that we are working backwards from derivative. So we've been talking about how we derive certain pieces. Now they want us to go backwards. And I'm going to jump into example 1, where it says if f of x equaled 2x, find a function that is the antiderivative of f of x. So we're working, as I said, we're working backwards. And so this 2, which is in front, then had originated as the exponent. So that should have been x squared. And then to just check that, 2 coming in front, multiplying by an x, 2 minus 1 is 1. Yep, okay, so this is definitely x squared. And then in the book, they say, okay, our f of x, because it just said find a function, any function, it could have minus 463, or it could have plus 2,000,009. I could put a variety of things here because when you derive any constant, it goes to 0 and drops off, and you don't need it in here anymore. So I could add anything I so choose to the end, because when I derive that, I go back to just the basic 2x. So that leads very much into part B, which is the integration. Now, integration is this little special curly Q at the front of a given equation. So in example 2, it says find the integration of the cosine of x. So I'm going to come back to this constant here when I solve this problem. So when I see this, I realize I'm working backwards. So how did I get to cosine? Well, it came from sine. So the original derivative should have been, or when I was asked to derive, it would be sine of x. And then you always put a plus c at the end of an integrated equation because it could have anything as a constant here at the end. And that is the integration thought process when we're dealing with these. And I'll go through some other examples and you'll get to understand how we work backwards, but this is just the beginning introduction to integration. Now, they did on page 220 their explanation about why we have the plus c, and they also show you back those original x, or the function of x plus the change of x minus f of x over that change of x. There is no corresponding definition of an indefinite integral of a function. So finding the integral of a function requires the ability to guess the answer based on experience with the derivative and the differential. And we check our guess by finding the differential or the derivative of our guess. So again, this is not, I mean, this one was pretty clear, but they're right. A lot of the times it's a guessing process and you might guess wrong. And then when you derive this, you don't quite get back to this. Okay, well then we need to fix what we just tried. So then example 2 says, oh, that was 2 I just did. Example 3 says, find the integration of negative sine of t. So where did sine come from? Well, it came from cosine. And what about that negative that was there? Well, when I derive cosine, I go to negative sine. So yep, keeping this as plain cosine t, checking it takes me back to negative sine, so I know I'm good. And I always have to put the plus c at the end because I could have any other constant added in there. All right, example 4 says, find the integration of e to the x. Oh, well, that one we know when we derive e to the x is e to the x. So that should be e to the x plus whatever the extra constant is. Example 5, I'm going to cram it in here even though I probably shouldn't, but it says dy over dx equals cosine of x, find the y. So obviously this is a derived, and so this is just another way of asking us to integrate. And so where did cosine come from? Well, again, It came from sine. So we have sine of x plus our constant that is always at the end.